Hi everyone, welcome to our 15th and last lecture. This lecture is on rotational motion, and it's going to be a combined lecture for both the calculus and the non-calculus students. Okay, so rotational motion. What is that? At the end of our last lecture, when we were working on the center of mass, I said that one of the things that comes out of a full analysis of linear momentum is this idea that if you have a bunch of masses that actually form a system. Okay, and these masses could be interacting loosely, like they might in a gas, or they can be interacting very tightly, the way the molecules might in a solid. But as long as they're just interacting with one another, you have something that forms a shape. Okay. Now, in what we're going to do, we're actually going to think of the shapes as solids. All right, liquids are for next semester and gases are for next semester. So think of the atoms or molecules or whatever the constituent components are as interacting, little masses that interact with one another. And I said, without giving a full analysis of it, that you could treat this extended object. First of all, it's a rigid extended object. Rigid because it's a solid, extended because not all the mass is at the middle. Okay, and it's an object. All right, so it's a rigid extended object. This rigid extended object, when it moves, you can analyze the motion as two things, or having two components. One is the motion of the center of mass, and the other one is the motion around the center of mass. And it's important to break it up that way, because if you had something like I had my remote, I gave the example of the remote. If I throw my remote up into the air, unfortunately I can't do this demonstration for you, but I think you can imagine the remote, the middle of the remote, that center of mass. If you had a little line there and you took a video of this thing as it went up into the air, and you follow the line, I followed the dot that indicates where the center of mass is, it would follow the parabolic path, exactly the way we studied it when we did 2D kinematics. But that doesn't fully describe the motion of this thing. Yeah, the middle of it would follow this parabolic path, but the object itself would rotate as it does that. Okay, and so the way to think about this is that you say, well, what's the motion of the whole thing? We'll talk about the motion in two parts: the motion of the center of mass, and we've actually studied that. That's everything we've studied up to this point in the course. And then the rotation around that center of mass. Okay, and so that rotation around the center of mass, that's the topic of our lecture now. Okay, so this is rotational. It's called rotational motion, and there's a rotational kinematics, there's a rotational dynamics, and there's also rotational energy and rotational momentum, although we call it angular momentum. All right, and so we're basically going to redo everything that we did in the course up till now, but we're going to redo it for rotational motion. And it's not as difficult as you think, because one, you've already seen it, and also we're not going to do a full rotational motion. We're just going to think about rotation in the plane. Okay, so when something is rotating, it could be rotating like this, and I'm trying to indicate that it's rotating in a plane, but it could also be rotating in a really interesting pattern where it actually is a three-dimensional. We're not going to do that. We're just going to think about rotation in a flat plane, so that yeah, the object is rotating, but everything about the object is like in a plane. All right, so if we do that, then things get pretty simple. All right, so what I'm trying to indicate here is, here's an object. Okay, and I don't even know what this object is. It's like a circle with a little handle on it, like that. Okay, and as this thing rotates around its center of mass, and there I put the dot there and I called it CM for the center of mass. As this thing rotates, you can see the handle is in one position at one time, and then in another position at another time. Now, I'm not showing in this diagram the motion of the center of mass, because that would make life complicated. Okay, so actually for most of this lecture, you could just think of the center of mass as being steady, or not even, just even ignored. Okay, so just concentrate on this handle. At t equals 0, this handle here is at one particular angle, it's in one direction, and then at a later time, say at t equals 1 second, 1 second later, the handle is at a different position here. And you want to say, this thing rotated, and you can say, well, how much did it rotate? And the answer would be the angle through which that handle rotated. Okay, so I put this dashed line to indicate the middle of the handle, and there's the position of the middle of the handle at t equals 0. There it is at 1 second, and you say, well, how much did it turn? It turned through angle theta, like that. Okay, and now you say, just like we did at the beginning of the course, I want a complete kinematics. I want a complete mathematical description of this motion, and the answer is tell me theta at all possible times, and I've given you a complete description of the motion. Okay, so that's what we're going to do. We're going to just redo the kinematics, and here it is. All right. Now, I'm not going to redo all the details because guess what? It's absolutely analogous to everything we've done before. So over here on the left-hand column, I've got linear motion. That's what we did in 1D kinematics. And here I have the rotational motion. In 1D kinematics, the equivalent of the angle was the position. You said, where is this thing at all different times? So where is it at 1 second? Where is it at 2 seconds? Where is it at 3 seconds? But maybe we could do better than that. Maybe where is it at 1 second? Sorry, 0 seconds, half a second, 1 second, 1.5 seconds, or even smaller gradations, whatever our instruments would allow for. If we get the position at all different times, that was a function. Okay, so x, this is basically x is a function of time. Here, it's not x that's a function of time, it's theta, the angle, which is a function of time. Okay, so this is just a mathematical notation saying theta varies with time. You give me a particular time, I plug it into here to this function, and out comes one and only one theta. Okay, at every time it's at 1 theta. All right. Then remember I said, well, then there's the linear velocity. I didn't call it linear velocity then because I didn't have to contradistinguish it with rotational velocity or angular velocity. And so I just called it velocity. But now, to be very clear, what I was really working on before was the linear velocity, and that's just the change in position divided by the change in time. How far did it travel? Divided by the time it took to travel. That was the average, and then if you squeeze delta t down to an infinitesimal, that becomes the instantaneous velocity. I'm not going to go through those details. They're not important at this point. Same thing with an angular velocity. Okay, so if you say, how much does the angle change per unit time, that's your angular velocity. Notice the symbol that I'm using for the angular velocity. It's the same symbol for the angular frequency, and that's because they are the same. It is. The angular velocity is an angular frequency. Okay. I didn't call it that before because it wasn't clear that your omega was forming part of a kind of a kinematics like this, but it is. All right. And so in this lecture, I'm going to call it an angular velocity, even though that's totally equivalent to angular frequency. And the reason I'm going to call it an angular velocity is because I really want to, work within the framework of kinematics. And in kinematics, you have position, velocity, acceleration. So you have an angular position, we'll call it an angle. Okay, you have an angular velocity and you have an angular acceleration. In complete analogy to your position, velocity, and of course the acceleration, which is the change in velocity divided by the change in time. Okay, so just to go over this column again, you have angle as a function of theta, angle as a function of time, and then your rate at which the angle changes divided by time, that's your angular velocity. The rate at which the angular velocity changes in time, that's your angular acceleration. Okay, and these quantities will become intuitively clear as I start to do problems. So right now, I just want you to see that these are in complete analogy to those. All right. Also, there's a way of relating linear and angular quantities, and we'll be making use of that later. So I need to remind you how you define an angle theta. Now this definition is in terms of radians, all right? So you know that you can work in degrees, you can work in radians, and there's other systems too. There's actually another one called gradients, which I don't know who uses them, but you could come up with different systems for measuring an angle around a circle. All right, and when we did polar coordinates, we mostly worked in degrees, because why not? Degrees are very natural and so on. But for this, we're going to have to work in radians. And here's why. If you go back to how radians were defined in the first place, you remember from your math class, you had a circle here. So this circle has a radius r like that. Okay. Now, if you start at some point on the circle and you travel a distance s along the outside, okay. Now, s is curved, because the circle is curved and you're traveling around the outside of a circle. You can think of this as like a track in a track and field, which is a circular track, and you're just walking along the track. The track is curved, but you're still traveling some distance along the outside of the circle like that, okay? So whatever that S is, we'll call that an arc length, okay? And the circle has a radius r. This angle theta here is simply defined as, in radians, the arc length s divided by r, okay? And I think that makes sense. The bigger s is, the bigger theta is going to be, okay? And so by the time you've made one complete circle here like that, you've traveled the full circumference of the circle, And do you remember what the full circumference of a circle is with radius r? It's 2 pi r. So when you go all the way around here once, s is going to equal 2 pi r. So 2 pi r divided by r is equal to 2 pi, and that's why one revolution is the same as 360 degrees is the same as 2 pi radians. Okay, so one complete revolution is 2 pi radians. All right, this relationship between the arc length, the radius, and theta only works in radians. Okay, it does not work in degrees. So that's why we have to work in radians. If you have something which is in degrees, you're going to have to convert to radians, and we'll see that in a minute. Okay, so we'll need that also. In addition to these, we'll need this as well. Okay, and just a note about the units of these things, because we want to make sure that we're getting the right units. First, theta is dimensionless. That seems strange at first. You go, well, didn't you just say that theta is measured in radians? Yeah, radians are actually dimensionless. Okay, they have no units associated with them because they're a ratio of two distances. S here is measured in meters. R is measured in meters, and so the meters cancel out. Okay, meters divided by meters is dimensionless. So theta is actually dimensionless. All right, that might seem strange right now, and you can certainly write radians in there, and that's fine. But you're going to see when I do these problems that I'm going to just take out the radians, and the units will just work out just fine anyhow. Okay, omega is delta theta by delta t. The delta theta, this is dimensionless, so you can just write 1 there. And delta t, that's seconds, so it's 1 over seconds, and that's hertz, okay? Or per second, like that, or 1 over seconds, or seconds to the minus 1, or hertz, okay? And guess what? Remember when we did angular frequency, we measured it in hertz? It's the same quantity. It's exactly the same quantity. And so, yeah, here it's hertz as well, okay? And then the angular acceleration, which is alpha, it looks like an A. Maybe I should just say how to draw that. It's actually the Greek letter alpha, and you kind of, I don't know, you kind of make like this swoosh like that. Like it looks like a little bit like a fish or something like that. So it's not quite an A, and I'll try to make it, clearly different than an A by showing it's kind of like shaped like that, like half an infinity sign, or an infinity sign with one end broken. Okay, something like that. Okay, so the angular acceleration is your change in angular velocity divided by change in time. The angular velocity, that's 1 over s divided by s, and so angular acceleration has units of per second squared, or seconds to the minus 2. Okay, so there we go with our units. Okay, so that's general kinematics, and I'm not going to go into the details of general kinematics because it requires calculus, etc., and it's difficult. Let's just do our special cases. So one of our special cases when we did 1D kinematics was the assumption of constant acceleration. So here we're going to do rotational motion assuming constant angular acceleration. And you won't be surprised, but the formulas look exactly the same as the ones before, but with theta replacing x, omega replacing v, and alpha replacing a. Okay, so take a look at the first equation. All right, this is equation 1. Equation 1 is just like our equation 1 when we did 1D kinematics. There we had x is equal to 1/2 at squared plus v naught t plus x naught. Here we have theta is equal to 1/2 alpha t squared plus omega naught t plus theta naught. Look at the substitutions. Where we had x, we put theta. Where we had a, we replaced it with alpha. Where we had v, we replaced it with omega, and there's theta again. Okay, and there you go. Okay, time is still the same between both of them. There's no such thing as an angular time or linear time. Okay, and so here's equation number 1. Theta is equal to 1/2 alpha t squared plus omega naught t plus theta naught. Here's equation 2. Omega is equal to alpha t plus omega naught. And then equation 3 is obtained from 1 and 2 by eliminating time. And that's omega squared is equal to omega naught squared plus 2 alpha theta minus theta naught. Okay. And it goes without saying, but the little naught there means the same as it did before, initial. So omega naught is initial angular velocity. Theta naught is initial angle. All right. Okay, great. Let's just jump into our problem. Okay, so these problems are basically objects which are rotating. And you might say to yourself, Isn't that like uniform circular motion? And you're kind of right, except that this is a generalization of uniform circular motion. So you can think of this as circular motion. Rotation is, whenever you have a dot on the object, that dot as the object rotates is going to etch out a circle. So yeah, there is a circular part to this, but it's not uniform. In uniform circular motion, the velocity, the tangential velocity, was constant. Here it's going to change. The object's going to start off slow and then it's going to speed up spinning, okay, or the other way around, okay. So the rate at which it spins can change. In other words, its tangential velocity will change, okay. And so this is actually a generalization of uniform circular motion, and you could see that in my very first problem. You would not have been able to do the first problem here using just uniform circular motion. So an old record player, I don't know if you've ever seen these, those old record players where you put the records on them, and the records would change and you'd have this needle which sat in there. Okay, some really old school stuff. And these record players, they would spin at 33 RPM. Okay, but when you turn them on, the record starts at rest and then it spins up. Okay, so an old record player spins up from rest to 33 RPM in 1.5 minutes. Okay, RPM stands for revolutions per minute. All right, so we'll look at that in a second. And I ask you two questions. All right, first is find alpha, find the angular acceleration. And I didn't say it here, but assuming that the angular acceleration is constant. All right, so find alpha. And the other one, part B, is how many times does it make, I'm sorry, how many rotations does it make in 1.5 minutes? So in the 1.5 minutes that it starts from rest and spins up, okay, how many times did it rotate when it did that? Okay, so what you need to picture, and hard for me to demonstrate, but it starts off rotating slower and then it goes faster and faster and faster and faster and faster and faster. Definitely not uniform. Starts slow, speeds up. Okay, so let's do this problem here, and you can use the equations 1, 2, and 3 in doing it. Okay, so the first thing is, actually the only tricky thing about these problems are the units. Okay, so here I give you RPM. Okay, a lot of things are measured in RPM. Centrifuges, if you look on Amazon, you can buy these centrifuges which are used to separate like blood samples and things like that. They spin, you put test tubes in them and they spin and they'll separate out your blood samples or whatever. You rate them on how fast they spin. That's usually given in RPM, revolutions per minute. Okay, now we're not working in revolutions per minute, we're working in hertz or per second. And so you say, well, how do I convert that? All right, well, let's do that. First, notice that the initial angular velocity is 0. The initial angular velocity is 0. When it's finally spun up, it spins up to 33 RPM. So 33 RPM, or 33 revolutions per minute, that's a measure of an angular velocity. That's how fast is it spinning. Omega answers the question, how fast is this thing spinning? It's spinning 33 revolutions, 33 times every minute. Okay? Now, usually you write RPM, but I purposely wrote this as rev divided by min, okay, to show you the two pieces that are going into this unit, RPM. One of them is the revolutions part, and the other part is the minutes part. The revolutions, we want to convert to radians, all right? And so we say, well, how much is a revolution? Well, I actually gave you that up above here. When we analyze this formula right here, in terms of the circle, I said that one revolution is the same as 360 degrees, is the same as 2 pi radians. There's our conversion factor. One revolution is equal to 2 pi radians. Great. So over here, making our conversion, our fraction for conversion, okay, we have revolutions in the numerator, so put one revolution in the denominator. One revolution is equal to 2 pi radians, and that'll eliminate revolutions and introduce radians. Okay, so there's one. And the other one is obviously you want to go from minutes to seconds, so 1 minute is divided by 60 seconds here. We'll do the conversion. Okay, the revolutions cancel and give you radians, the minutes cancel and give you seconds, so you get radians per second, and it turns out to be 3.454 per second. Okay, so great. There's two pieces we have already, the initial angular velocity, the final angular velocity in radians per second. Notice I even dropped the radians here. That's okay. You'll see that it'll work out just fine. Okay, and also we have the time. The time is 1.5 minutes, but we need it in seconds, and that's 90 seconds. So a minute and a half is 90 seconds. Okay, and I'm asking you to find alpha, You say, well, how do I find alpha? Well, you could choose equation 2. Looks like it's the easiest one to use here. Okay, so omega is equal to alpha t plus omega naught. Okay, so the final omega we found to be 3.454 is equal to alpha times 90, like that. And so that gives you an alpha of 0.0384 per second squared. Okay, and that answers question A. Question B was, how many times does it turn? Okay, so how many revolutions does it make? Let me just read it again. How many revolutions does it make in 1.5 minutes? Now, this question here is a little bit, the way it's worded is a little tricky. It's not hard to solve, but just the wording is a little tricky because you say how many rotations, and you look at these formulas in here and you go, well, which one of these symbols represents how many rotations? And so think about it this way. Don't think how many rotations, but think what angle did this thing turn through. So we know that if you make like a quarter turn, that's just like a pi by 2 radians, or half a turn, like 180 degrees, that's just pi radians. A full revolution is 2 pi radians. What if you made 2 turns? 2 turns would be 4 pi radians. 3 turns would be 6 pi radians. 4 turns would be 8 pi radians, and so on. Okay, and so basically, even if you've turned more than one complete turn, okay, you've done more than 2 pi radians, you're still building up theta. You're still like adding theta. So you could look at 2 turns, 3 turns, 4 turns, and so on. So if you solve for theta, that'll indirectly tell you how many revolutions you've made. It tells you the angle through which you turned, even if you turned more than one complete turn. And then if you divide out the 2 pi, that'll tell you how many revolutions you've made. So the upshot of that is, whenever you see the question, how many rotations does it make, think I'm solving for theta. Okay, that's what I'm asking for. How many rotations? Find theta. All right, so now that we've got that out of the way, we know that we're looking for theta. You say, well, do I want to use equation 1 or 3? You can't use 2 because 2 doesn't have any theta in it. And equation 3 is probably the easiest. You could use either one, but I just chose 3 here. So equation 3 says omega squared is equal to omega naught squared plus 2 alpha theta minus theta naught. And at this point, you say, well, what's my theta naught? Well, theta naught, that's like your x naught. That's like your starting position. There's no reason not to choose 0. Okay, so like remember when we had the car stopping and I said at the point where the car starts to stop, we'll call that x equals 0 because that's where we put the ruler. Well, here we don't have quite a ruler. We have the equivalent of a ruler, which is a protractor, around the outside of a circle, okay, measuring along the outside of a circle. And you could choose the 0 degrees at any point you want. So you say, you know what, at t equals 0, this thing is at theta equals 0. You can almost always safely do that, okay? And so we'll choose theta naught is equal to 0 and then substitute in all the numbers here. So what do we have? We have like omega, which we solved above. That was 3.454 squared. The initial omega was 0, and there was the alpha that we had above as well. And so solving for theta here, we get 153 radians. And I wish I'd broken this into 2 lines, but that's just, you just solve for this, you just get this piece right here, 155.3 radians. That almost answers the question, but I want to know how many revolutions, okay? And so that's why I multiplied by this fraction here, because it converts it. Remember, this fraction is always equal to 1, so you can always multiply it by it. So, if you solve this, you're working in radians, so you would get your theta in radians, 155.3 radians, but then we want to convert to revolutions or turns. And 1 revolution is 1 turn, okay? And so here we have radians on top. We want to get rid of them, put the radians on the bottom, 1 revolution on top, and multiply that through, and we get 24.7 revolutions. So in that 90 seconds, in that minute and a half, when I turn on the record player, it starts to spin up, it starts to spin up, it starts to spin up, it's spinning faster. By the time it's spun up to 33 RPM, it takes a minute and a half, it will have made 24.7 revolutions. Okay, so that answers part B. All right, now before I get to part C, I didn't ask it above. Part C is going to be relating the angular quantities to linear quantities. They're not independent of one another, okay? So angular quantities are like linear quantities in disguise and vice versa, okay? We'll see that all the way through this, actually. Even when we get to the end, when we do angular momentum, you'll see that, I'll have a linear momentum, but it's really like an angular momentum in disguise, okay? So you say, well, how does that work? How do I get my head around the linear quantities and angular quantities? And let me say, it always goes back to this formula right here, or this relationship right here. Okay, I can't stress hard enough how important it is to understand this conceptually. Okay, because over here we have S, which is the linear quantity. R is a constant. That's just a radius, and S is the linear quantity, and theta is the angular quantity. And the R there, like I said, is just a constant. So the angular quantity is related to the linear quantity by this formula here. And it doesn't just work for S and theta, it'll also work for velocities and acceleration. So it's important to conceptually understand why this formula is true. Okay, so now I'm going to be asking about a tangential velocity, and just to get your head around that before I ask the question, imagine that a record player actually has a radius of 15 centimeters. Those large record players, 15 centimeters sounds about right. A diameter of 30 centimeters across. It sounds about right for how big they were. And suppose it has a radius of 15 centimeters, and I have this little speck, this little dot. Maybe I just like take a marker and make a dot on the outside of the record. And as the record is turning, I ask a simple question: how fast is that dot moving? It's moving along the outside. How fast is it moving? And that's our tangential velocity. And I'll put a little t there because we're going to have some centripetal and tangential. So just to keep everything clear, this is tangential because it's along the outside. It's along the tangent on the outside. Okay, so we'll call that vt. And so there's a tangential velocity on the outside of the circle. And I think it's pretty clear that the bigger omega is, the bigger vt will be. Like if there were no angular velocity, if omega were equal to 0, then there'd be no tangential velocity because my dot wouldn't be moving. The faster omega is, in other words, the faster this thing is spinning, the faster the dot on the outside would be moving. Okay, it seems almost trivial to say that, it's so obvious, but is there a relationship? Is there a formula that will relate vt and omega? And of course the answer is yes. Okay, so here I've written out all the relationships between linear and angular quantities, so we have them all in one spot. If I were to ask a question, how far does that dot, so I've got my record player, put a little dot on the outside, and I say, how far did that dot travel? I know it's traveling in a circle, but you can measure how far that dot travels in the circle. Like, I don't know, you could say attach a string, and then the string will wrap around the outside of the record as it rotates. Okay, or maybe even better, picture the record like a drum, and it's wrapping this string as it does that. And I could ask the question, how much string did it wrap? Okay, so what distance did this dot travel along the outside? That's S. If I ask that question, it can be related to the angle through which the record turned by the formula S is equal to R theta. That's exactly the formula I gave above, but now I just rearranged it. I take the formula above and multiply both sides by R. Okay, so here S is the linear quantity, and it's related to the angular quantity theta. All right, so how far an object at a distance r from the center has traveled if the object rotates through an angle theta. Okay, so there you go. There's that. Now you say, well, what about the velocity? It's the same formula, but now just divide delta t on both sides. Okay, so if you have a change in the angle divided by a change in time, that's omega. Okay, and if you have a change in distance divided by a change in time, distance divided by time is your velocity. Okay, r is constant, so it doesn't factor into the change at all. It just stays the same. And so here, the equivalent of this formula here, which is just distance, the equivalent in terms of velocity is linear velocity is equal to r times angular velocity. Okay, so vt is equal to r omega. Okay, so this is how fast is an object moving at a distance r from the center, given that it's spinning with angular velocity omega. Okay, and then finally there's angular acceleration, but now it gets more complicated because there's two types of linear accelerations. There's a linear acceleration towards the middle, and that's your centripetal acceleration. That's exactly the acceleration that we analyzed with uniform circular motion, the centripetal acceleration. The centripetal acceleration is the acceleration which keeps the object on the circle. Okay, it's the turning acceleration. Remember, an object would want to move in a straight line because that's Newton's first law. But it keeps getting turned, it keeps getting pulled towards the middle by a centripetal force, causing a centripetal acceleration, and that's what keeps it on the circle. Okay, so the centripetal acceleration is what keeps this thing on the circle. It's towards the center, that's AC. Now, when we did uniform circular motion, we didn't have a tangential acceleration. And the reason is because the thing wasn't speeding up along the outside. It was always traveling at the same speed along the outside. But now, like in our record player example, it starts off slow and then it goes faster and faster and faster and faster and faster. And so it's accelerating around the outside. And that means that Vt is increasing, the tangential velocity is increasing, and that increase in the magnitude of the tangential velocity corresponds to a tangential acceleration at. So in generalized rotational motion, there's two pieces to the acceleration. A piece towards the center, which is the centripetal acceleration, and a piece along the outside, which is the tangential acceleration. The tangential acceleration follows the same pattern. Okay, so here we had Vt is equal to r omega. Well, if you take Vt and you just say, what's the rate at which Vt changes? That's at. That's your tangential acceleration. The tangential acceleration, by definition, is the rate at which the tangential velocity changes. And of course, that's got to equal r alpha, because what's alpha? Alpha is the rate at which omega changes. So the rate at which this equation changes leads to this equation there, which is the tangential. What about the centripetal? We did that already. Okay, AC is equal to r omega squared. Now, you may look at this equation here for the centripetal acceleration, and you might even go back to your notes about centripetal acceleration, and you look and you go, I don't see this equation there. Well, it's there in a bit of a disguise, okay? So remember that omega, I didn't rewrite this formula, but remember that omega can be written in terms of the period. Omega is equal to 2 pi over capital T. If you were to put that in here, this equation here would turn into the 4 pi squared r over t squared. A is equal to 4 pi squared r over t squared. So that equation, one of the three equations for uniform circular motion is really this equation here. It's the one that looks like 4 pi squared r over t squared. Now you don't need to know that. I'm just saying that even if you look at this and it looks a little bit like you haven't seen that before, you have, just in another form. Okay, so we actually did derive this already, and so there it is. So there are the two pieces. Okay, now why did I give it to you in this form and not in the form which is, has the period? And the reason is because we're working in angular velocities here. We're working in omega, so we want to continue working in omega and alpha. All right, there you go. So a little bit complicated when it comes to the acceleration, but for the distance that you travel along the outside, s is just equal to r theta. Okay, for the velocity that you're traveling along the outside, the tangential velocity, that's just equal to r omega. For the acceleration, two pieces: the acceleration towards the middle, the acceleration that keeps you turning, that's AC is equal to r omega squared. And for the acceleration along the outside, the tangential acceleration, that's equal to r alpha. Okay, so there's all you need to relate your linear quantities and angular quantities. Maybe just one more thing. You might say, why did you call this S and not D? Because usually we say D for distance travel or something like that. And I think I'm just doing that because in a lot of math textbooks they call the arc length around the outside of the circle S. Okay, so it's nothing more deeper than that. I just don't want to introduce symbols that if you looked in some other textbook you'd find different symbols. Usually in math they call the arc length S, and so I'm just going to call it S. But it is D. It is a distance. Okay. All right. Oh, also, because you have two pieces to the angular acceleration, okay, and they're perpendicular to one another. If I wanted the magnitude of the full acceleration, you might say, well, how do I calculate the magnitude of the full acceleration? These are two components of the vector, aren't they? And so you can combine them together just using Pythagorean theorem. Okay, we'll see that in a problem, so it's not that big a deal. All right, if you calculate these two together and you say, no, I want the total acceleration, not just any one of the components, the two components just combine using Pythagorean theorem. Okay, now we're ready for part C to the problem. Okay, how fast is a point on the edge of the record moving once it spins up to 33 RPM, and assume that the radius of the record is 15 centimeters. Okay, so the record is spun up. Okay, and so it's spinning at 33 RPM, and we found that 33 RPM was the same as 3.454 per second. Okay, the radius of the record player I just gave it to you is 15 centimeters or 0.15 meters. Okay, and I'm asking for how fast is the point on the edge spinning. In other words, I'm asking for the tangential velocity. That's equal to r omega. So we have 0.15 meters multiplied by 3.454 per second, like that, and you multiply the two together and you get 0.52 meters per second. Very, very easy to do. Let me just show you a little bit about the units. The units of r here are meters. The units of omega, I said, are per second, but remember I also said they were radians per second. So here you have radians per second. Now if you multiplied out meters radians per second, you get meter radians per second. You go, well, that's not a velocity. Yeah, it is, because remember, radians are not a unit. And so I know it seems a little weird, but you can add radians and remove radians wherever you need them. The reason we sometimes carry the radians in with the units, I tend to drop them, but sometimes people will carry in the radians. It's just to remind you that it's an angular quantity. That's it. But the reason radians drops out is because radians is a ratio of distance divided by distance. It's that theta is equal to s over r. S is in meters, r is in meters, so it drops out, giving a dimensionless theta. And so omega, you know, the angular part of omega is also dimensionless. The angular part of alpha is dimensionless. And so the radian part is dimensionless, and you can just add it or remove it from units. So even if you had put here, you know, like radians per second, and then here you would have gotten meters radians per second, you go, oh, well, radians are dimensionless, just drop it. Okay, you can't do, it's not really a unit. You can't do that with meters, you can't do that with seconds, but you can do it with radians because, like I said, radians are not really a unit. All right, now part D, what is the centripetal acceleration at t equals 0, and what is the centripetal acceleration at 1.5 minutes? See, now the equation I gave you for the centripetal acceleration depends on omega. All right, and if omega changes, that means the centripetal acceleration will change. All right, and so that's why this is still, even though the formula is the same, this is still really a different physics than we had before, because omega here has a functional, has a time dependency. Okay, and so you really can't use the 4 pi squared r over t squared because t is a fixed number. But here there's no real meaning to t, because, you know, as the thing spins, as it's spinning faster, the period becomes smaller, so that makes no sense, which is another reason to really think about the formula here like that. All right. So anyhow, I want that AC at t equals 0 and at t equals 1.5 minutes. Well, at t equals 0, omega 0, because it's just starting to spin up, and so it's not spinning yet. And if you do AC is equal to r omega squared, that just gives you 0 meters per second squared. Okay, I didn't show you how the units work out here to meters per second squared, but you'll see that in just a second. Okay, and at 1.5 meters, that's after the thing is spun up to the 33 RPM, omega is equal to 3.454 per second, and you plug that in here into the r omega squared, and you get that AC is equal to, here's the r, 0.15 meters, and here's the omega, the 3.454 per second squared. And when you work this out, you get 1.79. Notice the units, you get a meter, but then you have a per second squared, so it's per second squared there. Okay, so 1.79 meters per second squared. You start from 0, and the centripetal acceleration grows and grows and grows. It has to grow, because as it turns faster, you're going to need more centripetal acceleration to keep the thing on the circle. Okay. All right, great. So there's the story with the centripetal acceleration. What about the tangential acceleration? What is the tangential acceleration as the record spins up? Well, at all times between t equals 0 and 1.5 minutes, the tangential acceleration is going to be constant, because all of this is under the assumption that the angular acceleration is constant. Okay, so if the angular acceleration doesn't change, the tangential acceleration doesn't change. Here's the formula that relates the tangential acceleration to the angular acceleration. R is a constant. If alpha doesn't change, AT doesn't change. Okay, so just substituting in the numbers that we found above, the radius is 0.15 meters. Alpha we found to be 0.0384 per second squared, and that gives us a tangential acceleration of 0.00576 meters per second squared. That's quite a difference, okay, and that's typical of these kinds of problems. Notice the centripetal acceleration is much, much bigger than the tangential acceleration. Okay, well, I should be careful. The centripetal acceleration changes over time, but so it starts at 0 and it grows, but the centripetal acceleration will grow to a number typically much, much larger than the tangential acceleration. Okay, at 1.78 meters per second squared, that's like 1.8. What can you compare that to? You can compare that to the acceleration due to gravity, 9.8. Okay, so 1.8 compared to 9.8 meters per second squared. So this is a sizable acceleration. Okay, it's definitely something that you would feel if you were small enough to be on this record or whatever. You know, you'd be feeling something like roughly 1/5 of your weight, just due to the centripetal acceleration. But this number is tiny. Okay, and so when I ask for the magnitude of the full acceleration, it's not surprising that the tangential doesn't contribute at all. So if we were to do this, a is equal to the square root of ac squared plus at squared. Okay, the ac part would totally swamp out the AC part will be much, much bigger than the AT part. See, the AC part is just, it's roughly 2 there, right? And if you square that, that's roughly 4. But here you got like 0.005. And when you square a small number, you get an even smaller number. And so, if you did this on your calculator, you would find that you would just get 1.79 with maybe some decimals way out there, but nothing that you would keep it once you round off. Okay, so there you go. Basically, the fact that AC is so much bigger than AT means that the total acceleration is dominated by the centripetal and with almost no contribution from the tangential. All right. At this point, we're done with the kinematics. Okay, I've taught you everything that you need to know about rotational kinematics. If you recall, what we did after that is we moved on to dynamics, and dynamics was basically Newton's laws. And so you say to yourself, okay, great, now that we have this mathematical handle on describing rotational motion, can we ask what would cause rotational motion? Like why do things rotate the way they do? Why did that record player start at rest and then speed up? What caused that to happen? And so whenever you're asking for cause, not just like a mathematical description, like what is a mathematical description is like what is omega at this time? What is omega at that time? What is alpha at this time? What is alpha at that time? Something like that. Okay. Or what is theta at this time? What is theta at that time? Once you move past that and you ask the question, what caused this to do that? To do this motion, then you're moving into the realm of dynamics, and that's where Newton's laws come in. Okay, so there's an equivalent of angular. Uh, there's an angular equivalent of Newton's laws. All right. Now I won't go through all 3 laws again. Okay. Let's just look at the second law, and the linear form of the second law was that F net is equal to ma. And I put the little vector hats on there because the direction of A of the acceleration was in the same direction as the net force. Okay, and let's just remember what we had to do to work with this formula. We had to first calculate F net, and what was that? Well, we had a bunch of forces acting on an object, and we had to add them all together, and we had to add them all together as a vector. Okay, and then once we had that F net, we could divide out the mass, and we would get the acceleration. Okay, and that was basically F net is equal to ma. And then we would answer whatever we were supposed to answer. Okay, the rotational equivalent of that looks the same, but F is now replaced with tau, which is torque. Mass is replaced with this I, which is the moment of inertia, and A is replaced with alpha, which is the angular acceleration. Okay, which I mentioned here. All right. So what is tau and what is this I? All right, so let me describe them very briefly here, and then I'm going to give you formulas for them, and then we'll do problems. Okay, well, alpha I don't have to describe because I already described that for you. What is I? I is this thing called the moment of inertia. So in linear Newton's laws, okay, mass, the bigger the mass, the harder it is to get it to accelerate. Okay, so you apply a force, the bigger the mass, the less acceleration you're going to get. Okay, for the same amount of force. Say you have, you're not that strong. and at best you can push maybe, I don't know, 500 newtons of force. Okay, so that's the best you can do, 500 newtons of force. The bigger the mass is, the less acceleration you're going to get for those 500 newtons. It's the same thing with I. Only now we're not talking about getting something moving linearly. We're talking about getting something to rotate. Okay, so the bigger the moment of inertia is for an object, the harder it's going to be to get it to rotate. Now that obviously has something to do with mass, because the more mass there is, the harder it is to get it to turn. But it's not just the mass; it's how the mass is distributed. Okay, and you'll see that it turns out that the more mass you put towards the middle, towards the axis of rotation, I'll define that also for you. The more mass you put towards the axis of rotation, the easier it is to rotate. The more the mass is towards the edge, the harder it is to rotate. Okay, so I doesn't just involve mass, it also involves how the mass is distributed throughout the extended object. Okay, and then torque. Torque, you've probably heard this word in just in general. Okay, torque is like basically like a twist or an attempt to turn something. Like when you go to screw in a screw, you're applying a torque, you're applying a twist to your screwdriver. When you have a wrench and you want to tighten a bolt or loosen a bolt, you put the wrench and you apply a torque. Okay, and there are actually wrenches that are called torque wrenches. And I don't know if any of you worked with car engines, but like in a car engine, you've got like the exhaust manifold or the intake manifold, and these are put on with bolts, and you can't put the bolts too tight or you can't put the bolts too loose. You got to tighten them to just the right tightness, and there are these things called torque wrenches, and you can set the torque, and then they'll torque up to that amount, and then after that they'll slip. Okay, so it's basically that turning. It's a force which is applied in such a way as to get something turning. Okay, that's the easiest way to define a torque. Okay, so there's the idea. If you apply a twisting force to an object, then you're going to get an angular acceleration, but the amount of angular acceleration that you're going to get is inversely proportional to how much moment of inertia it has, how hard it is to get it to turn. Okay, so there's Newton's second law, but now in rotational form. And like I say this a lot in the course, but I want you to know that these things are not just like, I'm not just throwing these things at you out of nowhere. You can actually start from Newton's laws, do some mathemagic, and auto-pop the rotational version of it. So these two equations are not really different equations. They look different. You'll treat them as different, but actually the second one can be easily obtained from the first one by just some mathematical manipulation. Okay, so it's still Newton's second law, but it's Newton's second law recast into a rotational form. Okay, if you guys were physics majors, that's the kinds of things that I'd expect a physics major to be able to produce, because that's the depth and the deeper parts of physics. But for you guys, you're not physics majors, so it's not necessary that you know how that's done. But it's important to know that that the whole thing holds together logically. Okay. So how do we calculate I and how do we calculate the torque? Okay, let's start with the torque, because the torque is a little easier to, well, I don't know if it's a little easier, but it's I don't know, there it is. You have to know it as well. So what do I have here? Here I have, I guess you could think of this as a wrench, okay? And there's the head of the wrench, and this is the armature of the wrench here, like that. Okay, and we're trying to screw in a bolt or maybe loosen a bolt like that. And when this thing turns, it's going to turn around what we call an axis of rotation. Okay, so that dot there is an axis of rotation, and you say, well, I don't see it as an axis, it's just a dot. That's right, the axis of rotation is coming towards you. The axis of rotation, depending on its orientation, I'll be able to draw it in the plane of the paper, or I'd have to just draw a dot. But it's basically the axis around which the object rotates. Okay, so here the axis of rotation is coming out at you out of the screen, and you'd be rotating around that axis like that. This whole thing would rotate around that axis like that. Okay, again, if you need something to picture, just picture this as a wrench. There's a bolt in there, okay, and we're basically screwing that in. All right, and of course the wrench has an arm. There's the arm of the wrench like that, and I'm applying a force like that. Okay, now the force is going to cause the torque, but it depends on how I apply the force. I can apply the force in such a way that I get no torque at all. Okay, so there's actually three ingredients that go into a torque. Tau is equal to RF sine theta. There's the formula. And what are the three ingredients that go into the torque? Okay. Well, the first ingredient is the force. Obviously, if you apply a force, you're going to start turning turning your bolt. Okay. And the bigger the force, the more you're going to turn it. Okay. So the bigger the force, the bigger the torque. Kind of obvious. But there's a second ingredient, and that is the radius r. That's the distance. R is the distance from the axis of rotation to where I apply that force. Okay, so picture that you're trying to, loosen this bolt, and it's very difficult to loosen. If you apply the force very close to the axis, you're going to have to apply a lot of force to get this thing to turn. The further out on the arm you apply the force, the easier it's going to be to turn. Okay, and so the bigger R is, the more torque you get. The torque is going to depend on how much force there is and how far that force is being applied from the axis. Okay, and I think it's pretty obvious. If you apply a force here, you're not going to get as much torque as if you apply the force out there. And the further out you can apply it on the arm, the easier it's going to be to turn this. Okay, which is why we have an arm on a wrench anyhow. If there were no R dependency, then you could just grab the screw, and it'd be just as easy to turn the screw there as it would if you pressed it out on the arm. But that's not the way the world works. Obviously, the further out on this arm you apply the force, the more torque you're going to get, the easier it's going to be to unscrew this. Okay, so there are two ingredients. The third ingredient is this sine theta, or theta. Now remember that sine of 0 degrees is 0, sine of 180 degrees is 0, and sine of 90 degrees is 1. That's the biggest sine gets, is 1 at 90 degrees. When you apply this torque, okay, you can apply it at any angle you like. So here I showed some arbitrary angle theta. If r is the vector from the axis of rotation to where the force is applied, and F is being applied at that angle there, then theta is the angle between R and F, like that. Okay. Now, when we did, our first Newton law problems, and we attached all the forces at the middle, we were not worried about the extended nature of the object. But here we are worried about the extended nature of the object, and so it's important that you specify where on the object the force is being applied. So that wasn't an issue before because we weren't worried about rotational motion, but now we are. So what we want to do is we want to say, yes, this force is being applied at a distance r from the axis of rotation and at an angle theta, like that. Okay. Now, why did I tell you about those 0, 90, and 0 here? When theta is 90 degrees, that is when F is perpendicular to R, that's when you're going to get the biggest torque. Okay, so if you push perpendicular to the arm, so the arm is out like this and you're pushing perpendicular to the arm, that's when you're going to get the biggest torque. Okay, if you pulled straight out, like, imagine grabbing the arm here and you don't turn it, like pushing it 90 degrees like that. You pull straight out, well, then that's not going to have any turning action at all. Okay, or conversely, if you push straight in, that's not going to have any turning action. So if you pull straight out, then the angle in there would be 180 degrees. Sine of 180 degrees, 0, no torque. If you push straight in, then the angle would be 0 degrees, and sine of 0 degrees is 0, no torque as well. Only when R and F are 90 degrees do you get the maximum possible torque. Okay, now that's kind of obvious, intuitively obvious, and if you've ever opened a door, you realize that all of these components are coming into play there. Take a look at where the doorknob is. The doorknob is as far from the hinges as possible. Okay, so that's your R. You want to make R as big as possible. So you take a look at a doorknob, and I'm looking at my door over there. The doorknob is on the opposite side of the hinges. The hinges are the axis of rotation. The doorknob is where you're going to be applying the force. Also, when you open the door, you push perpendicular to the door. You pull perpendicular to the door, and that's your sine theta piece, like that. Okay, so there are three ingredients that go into a torque. A force does cause a torque, but if R is 0 because you push right on the axis of rotation, or if you're pulling in the wrong direction or pushing in the wrong direction, your force, you might be applying a lot of force, but it's not giving you any torque at all. Okay, so there you go. There's the formula for a torque. We'll need that in a minute, and that's the torque due to one force. Go back up here. We'll notice this is tau net. That means if there's more than one force, there's more than one torque. You'd have to add up all the torques. Okay, and torques are a vector, but they're an easy vector for the problems we're going to do. because all of our rotations are in the plane, and so we only have to worry about two different directions, clockwise and counterclockwise. Okay, so torques also have a direction associated with them, but we're just going to worry about whether they're clockwise or counterclockwise. Okay, and so that makes it a lot easier. We're not going to have to decompose torques into the x and y components or anything like that. We're only going to have to say, does this torque want to turn something clockwise, or does it want to turn it counterclockwise? If you take a look at this force here, okay, here's the axis. If you were to apply this force and this thing were free to turn around that axis, this force would want to make the object rotate counterclockwise, so this will be a positive torque. We'll see that in a problem. If this is a little bit confusing right now, we'll see it in a problem. But basically, you look at your force and you say, does this force want to turn it clockwise, or does it want to turn it counterclockwise? Counterclockwise will be positive, clockwise will be negative. All right. Well, here's the other piece, the moment of inertia. Okay, the definition for the moment of inertia is I is equal to, and now if you have a bunch of point masses, m1r1 squared plus m2r2 squared plus m3r3 squared, and so on. Okay, so there's the formula. m1, m2, m3, these are all point masses that make up the extended object. So if it's like, I don't know, like my remote here, you say, well, what are all the little m's there? Well, you could go right down to the microscopic level, right down to the molecules. Okay, not that you have to do that every time, but you could think about it that way, and then you could calculate the moment of inertia that way. Okay, and the r's here are basically the distance from the m's to the axis of rotation. So you just say, how far is m1 from the axis of rotation? That's r1. How far is m2 from the axis of rotation? That's r2, and so on. You put them all together and you get your moment of inertia. Okay. Just one thing, you got to watch the definition for the moment of inertia. Don't confuse it with center of mass. Okay, so usually on a test I'll have an object and I'll ask for the center of mass and the moment of inertia. Just be careful to apply the correct formula in the correct place. Okay, so there we go. Let's just do a problem. And here's my first problem, my first example. It's one of my funny dumbbells here. So I've got 4 masses: 1 kilogram, 3 kilogram, 2 kilogram, and 1 kilogram at a distance of 1 meter, 1 meter, and then 2 meters, like that. They're displaced from one another according to those distances. And for part A, I'm going to say put the axis of rotation perpendicular to the masses, like that, and passing through the 3 kilogram mass, like that. And for part B, I'm going to say calculate the moment of inertia of this thing, but now move the axis of rotation through the 2 kilogram mass. Okay, now it turns out that when you move the axis of rotation around, you're going to get a different I. You're going to get a different moment of inertia. The moment of inertia doesn't just depend on the masses, but where the masses are relative to the axis of rotation. You'll see that you get 2 different answers for this. Okay, so when I do these problems, when I give you these problems, I'm not only going to have to give you the mass distribution, but I'm going to have to tell you what axis I expect you to calculate it around. If I don't tell you that, then the problem is ambiguous, because you say, well, do I want my axis here? Do I want my axis here? Do I want it there? And not only that, I put my axes perpendicular, but your axis could be on an angle. They could be in all sorts of funny ways. Okay, I won't throw problems like that at you because it makes them more complicated, but I just mentioned that your axis could be anywhere, really. And so in this particular problem, part A, the axis of rotation is perpendicular to the line of the masses here, like that. It's perpendicular to it. That dashed line is the axis, and it passes through the 3 kilogram mass. And for part B, it passes through the 2 kilogram mass. Okay, let's do this problem. So for part A, we'll call this one M1. So M1 is 1 kilogram, and it is at a distance. M1 is, the 1 kilogram is 1 meter from the 3 kilogram. And so R1 is 1. Okay. Next, there's the 3 kilogram mass. So I write 3 there. And how far is the 3 kilogram mass from the axis? It's right on it. And so 0. Okay. So that's interesting. When a mass is right at the axis of rotation, it has no moment of inertia. Okay. It's very easy to turn a thin rod, okay, or where all the masses accumulated around the axis. That's easy to turn. It's when the mass is distributed far from the axis of rotation that it gets harder to turn. Okay, and so the 3 kilogram mass, because it's at a 0 distance from the axis of rotation, will actually have no contribution to the moment of inertia. Okay, and then M3 here, we could say that's the 2 kilogram mass, and it's at a distance of 1 meter from the axis. Okay, and then finally we have this 1 kilogram out here, but it's at a distance of 2 plus 1, or 3 meters from the axis of rotation. And just work that out, it turns out to be 12 kilogram meters squared. Okay, so those are the units for moment of inertia, kilogram meters squared. There's no abbreviated unit. Okay, and the dimensional analysis is easy. The mass gives you kilograms, units of kilograms, and the R gives you meters, and that's squared. Okay, so kilogram meters squared. Now, what happens if I move my axis? So if I move my axis to here, then the 1 kilogram is going to have a distance of 2. The 3 kilogram is going to have a distance of 1. The 2 kilogram is going to have a distance of 0. And the 1 kilogram here is going to have a distance of 2. And that gives you this. Okay, so the 1 kilogram was at 2 meters. The 3 kilogram is at 1 meters. The 2 kilogram is at 0 meters. And the 1 kilogram is at 2 meters. You work this out, and now it's 11 kilogram meters per second. 11 kilogram meters squared. Okay. So not a big change, but still it's different. The moment of inertia when the axis was in one place was 12, and when we moved it, it's 11. Okay, and so yeah, if I move the axis around, it'll change. In fact, you could try this, just to practice. Put the axis of rotation around this 1 kilogram here. Okay, in which case the 3 kilogram is at 1 meter, this one is at 2 meters, and this one out here would be at 4 meters. You'll see that you'll get a much bigger number still. Okay, and there's this neat little theorem. Again, I'm not going to prove it to you, but I'm just going to mention it because it's good to know. The smallest moment of inertia you'll ever get is when your axis passes through the center of mass. Okay, so like one of the things I could have asked you to do in this problem is find where the center of mass is. Okay, turns out to be over here, somewhere around there, at about 1.6. Okay, meters from here. If you start there to there, it's about 1.6. And you could say, well, what would happen if I put my axis of rotation right through the center of mass? That's when your moment of inertia is the smallest. Okay, so the moment of inertia is the smallest when the axis passes through the center of mass. You move the axis out here, it'll get bigger. You move the axis out here, it'll get bigger still. Okay, and you can put the axis even outside of all of them. If you extended this bar, and it'll get even bigger still. Okay, so there you go. There's a one-dimensional problem, axis of moment of inertia. What if you had two-dimensional problem with moment of inertia? And again, I got to make these problems easy for you, because if I put the axis in some strange direction, life will get really hard. So I won't do that. I just want to make sure you understand the concepts. And so here I have 4 masses. M1 is 3 kilograms, M2 is 5 kilograms, M3 here is 4 kilograms, and M4 is 7 kilograms. Okay, and here they are along the x-axis and the y-axis. And I put this axis of rotation in the plane. Okay, so it's in the same plane as these 4 masses, and it's at 1.5, x is equal to 1.5 meters, right along there. So here's x equals 0, here's x is equal to 1.5, and there's my axis like there. And go, how does this thing rotate? Well, you'd have to picture it rotating out of the plane. So this mass here would come out towards you, that mass there would go into the page, or into the screen, and it would go in and out, in and out, and in and out as it rotates around this axis. This guy would go out and then in and then out and then in, like that. And same with this one. This would go in and then out, in and then out. Okay, and the same thing with that one. Okay, I can't draw that for me. I can't even show it to you with the cursor, because you got to picture it coming out of the screen. Okay, but they're rotating around this, and now you're going to use the same formula. Same formula still applies, but you ask yourself the question, how do you measure R's? Okay, and the answer is R is always measured as the shortest distance from the mass to the axis. So you start here at the 3 kilogram. You say, well, what's the shortest distance? Well, the shortest distance is 1.5. Same thing for this 4 kilogram up here. You say, what's the shortest distance? It would be from there, follow my cursor all the way to there, 1.5. You could say, well, should I measure it down there? No. Should I measure it to any other point there? No. You actually measure what's called the perpendicular distance, which is also the shortest distance, and it's the shortest distance between the mass to the axis of rotation. The reason you're picking the shortest distance is because when these things are rotating, they make circles, and it's really the radius of that circle. So when this rotates around that axis, it's going to rotate with a radius of 1.5 meters. When M2 equals 5 kilograms, when M2 rotates around that axis, it's going to rotate with a radius of half a meter, 0.5, like that. When the 4 kilogram here, m3 equals 4 kilograms, when that rotates, it's going to rotate with a radius of 1.5. And when the 7 kilogram rotates, it's going to rotate with a radius of 0.5. Okay? And so those are the R's that go into here. All right? So now, M1 has R1 of 1.5, M2 has R2 of 0.5, M3 is 4 kilograms, has an R3 of 1.5, M4 is 7 kilograms with an R4 of 0.5. Okay, and here I'm trying to show you how you measure the distance between M3 and the axis. It's that perpendicular distance like that. Okay, well, just plugging in all the numbers, it's easy enough math, and you get 18.75 kilogram meters squared. Okay, great. Now we did point masses, the moment of inertia for point masses in 1D. We did the moment of inertia of point masses in 2D. What about the moment of inertia of objects, like rings or spheres and things like that? And there are equations for those too. These are the moments of inertia for various objects. They're useful, especially if you're going into kinesiology, because the human body is made up of bones, and bones are like rods. And these are rods which rotate around axes of rotation. Here my elbow is an axis of rotation, and my arm is a rod. And so all of the physics that I'm showing you, if you're heading towards kinesiology, is going to be making use of the moment of inertia of something like an arm. These things are actually either measurable, or you can calculate them using the formulas that I'm going to give you right now. Okay, so we're not going to study a lot of different shapes. You can actually, there's an entire Wikipedia page dedicated to the moment of inertia for different shapes, but we just need a few of them. One of them is a ring. So here's a ring, and all the mass is on the outside of the ring, here like that. And we're going to have an axis of rotation right in the middle of the ring, coming straight out at us, so in and out of the screen, like that. And the ring has a radius r, I called it capital R, and it has a mass capital M, like that. The moment of inertia of this ring around this axis, as shown, is going to be I is equal to mr squared. So there's the formula for the moment of inertia of a ring with the axis through the middle, like that. Okay, now what if you have a disc or a drum? Okay, the height or the thickness of the disc doesn't matter, so that's why you can make this thicker, and if a disc gets thicker and thicker and thicker, it essentially becomes a drum. So either a disc or a drum. This whole disc has a mass capital M, the disc has a radius capital R. The moment of inertia of around an axis which goes through the middle of the disc perpendicular to the plane of the disc, as shown, okay, is going to be 1/2 mr squared. All right, so there's the moment of inertia of a disk with the axis of rotation as shown. Okay, remember, if I move the axis of rotation around, this formula won't work. So this formula not only depends on the shape, but also the fact that the axis of rotation goes through the middle as shown. Okay, so keep that in mind. All right, what about a rod? All right, so here's my rod, and I'm going to put my axis of rotation around one of the endpoints. This is like your arm. The axis of rotation is my elbow, and here's my arm going up and down like that. Okay, and so the arm is like a rod of length L and mass M, and the axis of rotation is at one of the endpoints, the elbow. The moment of inertia would be 1/3 ml squared. 1/3 ml squared. Okay. What if you were to put the axis of rotation in the middle? Well, now I can't do that with my rod, but imagine like a baton of some kind. So you got a baton, but you grab it in the middle and you make it rotate around the middle. Okay, and then the moment of inertia is 1/12 ml squared. So if you move the axis from the edge to the middle, you significantly decrease. You decrease the moment of inertia by a factor of a quarter. Okay, so it's 1/12 ml squared if the axis through the middle. Okay, what if you put the axis right along the rod itself? Well, if the rod is very thin, that's like putting all the mass along the axis. You'd have no moment of inertia. Okay, and you might get crazy here. You say, well, what if I make my axis at some angle? Well, then this formula doesn't work. Okay, you could still calculate it, but it'd be a fairly complicated calculation. Okay, so we're just going to stick to these shapes and these axes. Okay, and one more, and that is a solid sphere. This is like a ball, but not like a tennis ball, which is hollow in the middle. More like a lacrosse ball. Okay, so like a solid ball, all of uniform mass. Okay, all of uniform density, I should say. And for a solid sphere, the moment of inertia is 2/5 mr squared, 2/5 mr squared, okay? And here, I didn't draw the picture because it's hard to draw a picture, but here the axis of rotation is right through the middle of the sphere. The axis of rotation has to pass through the middle of the sphere. Okay, so maybe I should have written that in writing there, but you know, there it is. It's hard to draw, so I didn't draw it. Okay, now all of these formulas can actually be derived from this formula here, you know, the m1r1 squared plus m2r2 squared and so on. You can actually start from that and derive all of these formulas. I'm not going to do that for all of them because it's, again, one of these things that requires some fancy math. It requires calculus. But I'd like to show you, at least for the ring, that the formula for the point masses really is the same as this formula. Just to give you some intuition, it helps a little bit, I think, and to understand where these formulas are coming from. Let's show why the moment of inertia for a ring is mr squared, like that. So let's take a ring like this, and let's chop the ring up into a bunch of little m's. So m1 is just like this chunk of the ring, and m2 is that chunk of the ring, and m3 is that chunk, and m4 is that chunk, and so on. Okay. So we cut the ring all up into these little masses, okay? And now we say, well, I know how to calculate the moment of inertia of a bunch of little masses. It's m1r1 squared plus m2r2 squared plus dot, 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 because there could be millions of these around here, okay? It depends how small you chop the ring, okay? And the next thing you say is, but all the r's are the same. I know I called it r1 because it's the radius for m1, and I called it r2 because it's the radius for r2. But the radius for R1 and the radius for R2 and the radius for R3, all of them are just capital R because every single mass is the same distance from the axis of rotation. It's in the middle. It's the middle of the ring. The ring is a circle. The circle has a center, and all the masses are the same distance from that center, capital R. So now I can replace R1 squared with just R squared, and R2 squared with just R squared, and R3 squared with just R squared. Then I can factor out the R squared, and I get m1 plus m2 plus m3 plus dot 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 times r squared. But if I add up all the little masses, what do I get? The total mass, and that's equal to mr squared. Okay, and so what did I do? Basically, I showed you that if you apply this formula, which is the definition of the moment of inertia for these point masses, when you apply that to a ring, you get the formula that I gave you above. Okay, you could do that with all the shapes, and you'll get the same answer. Now, the reason I point this out is not just to show the consistency, but again, if you go into kinesiology, you might have some shape, you know, some bone. And the bone is not exactly a rod. You know, it's thicker at one end, it's a little thinner, and then it's thicker, and there are different shapes to it, and so on. And you might say, you know what, I need something better than my 1/3 ml squared formula. I need something a little bit better than that. Well, you know what, you can treat the bone itself, even though it's a solid bone, you can treat it as being made up of segments. You can say, well, this segment is at this distance and it weighs this much, and this segment is at that distance and it weighs that much, and you add it up, and you should get a better estimate of the moment of inertia of this particular segment of your arm, okay, like that, okay? And you can always compare it to the 1/3 ml squared just to see, you know, how much more accurate one is than the other. All right, so okay, there we go. There's the story for how to calculate I. Don't lose sight of the bigger picture. We're going to do tau. We're doing this. Scroll all the way back up here. All right, we're going to do tau net is equal to I alpha. So tau, you use the torque formula, you add up all the torques, and you get net torque. I, you make use of either the point formulas or the one of the other formulas that I gave you for the different shapes, and that'll give you I. You take tau and divide it by I, and that gives you alpha. Okay, so that's what we're doing. That's why I went through all those details. It's just basically to be able to apply this formula here. Okay, so we're ready for our first problem. Here we go. It's a rod. Okay, so we have a rod. The rod has a full length of 15 centimeters from end to end here, like that. 15 centimeters. And I apply two forces. I apply one force at 5 centimeters from one end. That's 3 newtons. And I apply it perpendicular to the bar. And I apply another force at a distance of 10 centimeters. And that force is applied at this angle here, like that, and such that it's at 120 degrees from the bar, like that. Now, if it's 120 degrees here, it's 60 degrees over there. In case you think maybe I'll get confused about whether I use the 120 or the 60 degrees, sine of 120 degrees sine of 60 degrees are exactly the same. Okay, so you can't go wrong like that. It's symmetrical about the 90-degree mark. Okay, so we'll use the 180. All right, and the whole thing is going to be forced to rotate about an axis which is at one of the endpoints like that. Okay, so if you want to picture how this would work, like, I mean, you've got a bar here like that. Maybe you could put like a little nail and just like nail it into a board. And this rod is free to rotate, but it's free to rotate around that point there like that. Okay, so it's free to rotate around one of its endpoints. Okay, and I ask a series of questions. The first question I ask is find I. Then I'm going to ask you to find the individual torques. There are two forces, so there'll be two torques. Then I'm going to ask you to find the total, the net force, the net torque. Okay, and then from the net torque and I, you should be able to find alpha. All right, so let's start off. The first thing you do is you say, how do I get I? And I don't have a bunch of point masses. This is an I for a shape. The shape is a rod. The axis is at one of the endpoints. And so you say a rod, axis of rotation at an endpoint, the formula is 1/3 ml squared. So you should have these memorized, these formulas memorized for a test. Okay, so the moment of inertia is 1/3 ml squared for a rod rotating around one of the endpoints. The mass of the rod, I think I give it, yeah, I give it here, it's 1/2 kilogram. Okay, so over here we plug in a 1/2 kilogram, and the length was 15 centimeters or 0.15 meters. So there I converted it to 0.15 meters. Okay, and multiply that all out, I get 0.00375 kilogram meters squared. Okay, so there's the moment of inertia. It's a small moment of inertia, but it's a fairly light rod. And there we go. Okay, now what? Now I say find the torque for each of the forces. Okay, so for the 3 Newton force, the torque is going to be given by tau is equal to r of sine theta. All right, so now we have to just concentrate on that 3 Newton force and say what's r for that 3 Newton force. Well, let's look at the picture again. How far is the 3 Newton force applied from the axis? Well, the distance from the axis through the 3 Newton force is 5 centimeters. And also we'll need the angle between the r vector, which is where my cursor is going back and forth here, that's the r vector, and f, up and down like that, that's 90 degrees. Okay, and so r of sine theta, r is 5 centimeters or 0.05 meters. F is 3 newtons, and sine and the angle was 90 degrees. This gives you 0.15 newton meters. Okay, so there's the magnitude. Almost done. Next, we have to say what the direction is. It turns out to be counterclockwise, which will take us positive, but let's see why. Okay, so if we go back to the diagram, here's the rod. Remember what I said? I kind of nailed the rod at one end there, so this rod is free to spin around that axis right there. If I ignore the 7 Newton, just concentrate on the 3. Pretend the 3 Newton is the only force that's being applied. If I apply a 3 Newton force and I push up, this thing is going to want to rotate up like that. And it's going to want to turn like that. Just imagine I continue to apply that 3 Newton, always perpendicular to the bar, always perpendicular to the bar. It's going to rotate like that. And that rotation is counterclockwise. Okay, so the way to identify the sense or direction, usually when it's rotation, we call it a sense, or you could also say direction. But if you hear me say sense, I mean direction as well. So you just ignore all the other forces. You say, let me pretend there's only this one force, and that it's forced to rotate. The object is forced to rotate around that axis. And so if I just apply this 3 Newton force perpendicular to the bar, and it rotates around that axis, that part can't move, then it's going to rotate up, and it's going to go around and around and around. So you got to picture the bar. I don't know if I can, like this, and it's going to be like that. Okay, well, I guess it's the other way, like this. Okay, all right. Okay, so students sometimes find that a little bit hard to get, but if you think about it for a bit, you'll get it. Okay, so that was counterclockwise. That's going to be a positive torque. The other one, the 7 Newton, is r of sine theta again, but now it's applied at 10 centimeters, which is 0.1 meters. F is 7, and the angle is 120 degrees. Again, if you had made a mistake and said you measured the angle to the other side of the rod, you would have put 60 in there. Sine of 60 degrees is still the same as sine of 120. Try it on your calculator. You'll see that it works out. And so this will give you 0.6062 Newton meters, but this one is going to be counterclockwise, which is negative. And let's see if we can convince ourselves of that. So over here the axis is right here. It's the rod is tied down there. We press down here. Even though this is at a kind of an angle like that, it still has a perpendicular component which is down, which will cause the rod to start turning down here like that, and then around and up on the other side and around like that. And that's a clockwise sense. And so that torque is clockwise, and clockwise is negative. Okay. So there we go. There are the two torques. The 3 Newton gives you 0.15 Newton meters counterclockwise, and the 7 gives you 0.6062 Newton meters clockwise. Okay. Part C was calculate the total torque. Okay, so tau net is going to be the sum of all the torques. The 3 Newton, that came in positive, counterclockwise. The 7 Newton torque came in negative, and so when you add the two together, you get that the net torque is going to be negative 0.456 Newton meters clockwise. All right, because it's negative, because the total was negative, that's a clockwise force. All right, so great. Now we have the net torque. We have I, the moment of inertia from above, and so we can simply calculate alpha, because that was part D. Calculate alpha. Alpha is going to equal tau net divided by I. Tau, I kept the negative sign in there. Okay, divided by the I, that gives you a negative negative 121.6 radians per second squared. And so you get quite a bit of a angular acceleration. You get an angular acceleration of 121 per second squared, and it's negative, which means that it's actually going to be in the clockwise direction. Okay, so the 7 Newton force actually kind of beats the 3 Newton force. These two are trying to rotate them in opposite directions, but the 7 Newton wins out, okay? And so it causes the whole thing to ultimately rotate clockwise. All right. And there you go. Okay. So there it is. There's a problem with rotational dynamics. In other words, applying Newton's second law in rotational form to rotating objects. All right. And if you go back to the whole course, after we finished dynamics, the next thing we did was energy. Okay, and so now rotational energy. Let's take a look at that. So rotational energy, I don't really have to teach you all about the work energy theorem again. With rotational energy, it just leads to one modification, and that is that your total kinetic energy isn't just due to the motion of the center of mass. The kinetic energy, when it's just a point mass, you know, and I mean point mass means there's nothing rotating, the kinetic energy was 1/2 mv squared. But now there's two motions, there's two kinetic motions, okay? The center of mass is moving, and we usually call that the linear kinetic energy, okay? But then also the whole thing is rotating around the center of mass, and so there is a rotational kinetic energy. And so the total kinetic energy has now two contributions. A contribution from the motion of the center of mass, 1/2 mv squared, and a contribution to the rotation about the center of mass, 1/2 I omega squared. Okay, so in all of our energy problems, for the kinetic energy, you don't just write 1/2 mv squared, you write 1/2 mv squared plus 1/2 I omega squared. All right, so that's the first point. Okay, and again, I won't prove this, but you know, if you had some rigid object and you could see that it was moving, you could actually calculate the 1/2 mv squared for all the little point masses, collect them all together, and find that you're going to get 1/2 mv squared for the center of mass motion, and then the residual part would be the 1/2 I omega squared for all the rotational motions. In other words, these two are not in contradiction to one another, just like you saw me go from the point for the moment of inertia, the definition of the moment of inertia in terms of point masses, and then you got this, you know, the formula for the ring. You could do the same thing here. You could start with the kinetic energy for point masses and actually prove this other formula comes out of it. Again, I just mentioned this for consistency, to say that, you know, this is not something that's falling out of the sky. I'm not just making this up. These are all part of consistent physics. Okay. So there you go. That's going to be the first modification. The second thing is that while this is true in general, we often want to apply this particular formula to a wheel, a rotating wheel, which is rotating without slipping. Okay, so what does that mean? What is the physics behind a wheel that is turning without slipping? What do we mean by this without slipping? Okay, and this is a little tricky, but once you get it, you're okay. But if you're sitting here, if you're standing here on the ground, and this wheel rolls by you, this is a huge wheel that's rolling by you here, okay? And as this wheel rolls by, it's not slipping. What would you see if you looked at different points on the wheel? Okay, well, if you looked at the point of the wheel where it touched the ground, you would actually see that the wheel at that point where it touches the ground has a zero velocity. That sounds shocking the first time you hear it. But think about it this way. Think about the tires of your car. The tires of your car, where they're touching the ground, they can't be moving across the ground, because if they were moving across the ground, they'd be skidding. They'd leave skid marks. So when the wheel, I know it's moving, but at that instant when it touches the ground, it has a zero velocity. So the bottom of the wheel, the point of the wheel that touches the ground, has zero velocity. Okay? The axle of the wheel, that is its axis of rotation, okay, it's actually moving at some velocity v. All right, so there, that's moving at velocity v. It turns out, if you think about this, the top of the wheel would have to be moving at a velocity twice v. Okay, so there you go. There's this wheel turning. I gave the wheel also a radius r, and I said that the wheel had an angular velocity omega. Is there a relationship between the velocity of the middle of the wheel, the axle, and omega? And the answer is yes, there is a relationship between the two. Okay, and you can't just guess, even though it turns out to be the same as the tangential velocity formula above. You actually have to prove that there is a relationship, and I'll show you when this formula actually breaks down in a minute. But why does this formula even work? Why does this v is equal to r omega work with a wheel that's rolling without slipping? Well, the way to see that is to sort of change your perspective a little bit. Imagine, instead of standing on the road as the wheel rolls by, imagine running beside the wheel as the wheel is rolling. Okay, so the wheel is rolling and you're running right beside it at the same speed that the wheel is moving. If you look at the axle now, the axle is not getting ahead of you, it's not falling behind you, it's right beside you all along. And since the axle is always beside you at every point, the velocity of the middle of the wheel is zero. Okay, so don't picture the ground, just picture you and the wheel. Okay, just picture you and the wheel. Because as soon as you start to bring in the ground or the background, your brain gets all messed up and you think things are moving. No, 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 no. You and the wheel are running together. And so you're moving forward and the wheel is moving forward. And so if you look to your side, there's that axle, and it's not getting ahead of you. It's not falling behind you. It's always beside you. It's always beside you. So it looks like it has a zero velocity. It's not getting ahead or behind. Okay, so it has a zero velocity. Well, if this is zero, that's like subtracting v from this diagram, then the ground is moving behind you. It's falling away from you at velocity v. And the top of the wheel is moving forward at velocity v. So you could see that the tangential velocity of the wheel now is v, both the top and bottom. Well, if the tangential velocity is v, and it has an angular velocity omega and a radius r, well then v is equal to r omega. Okay, so even though we made use of the formula of tangential velocity, we really had to do it only in that perspective where you and the axle are moving together. Okay, so there it is. There's the formula that relates the velocity of how fast the axle of the wheel is moving and its angular velocity around that axle. Okay, let me show you that this formula doesn't have to be true when you're not slipping. Okay, so this only works without slipping, without skidding. Okay, and here's why. Everyone that's driven a car has had this experience. You get up in the morning and it's all ice, and you step on the gas and your wheels are spinning, but you're not going anywhere. Not a good feeling. Okay, so you're stepping on the gas and the wheel's spinning, 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 but you're not going anywhere. Obviously you're slipping, the wheel is slipping. Well, there's a case where you have some omega. It can even be a very big omega, because it could be spinning very fast. You're desperately trying to get out of this rut that you're in, and you're not getting out because it's all ice. So you've got a big omega, but what's your v? Zero. Okay, and in that case, if you look at this formula, omega is big, but V is 0. Well, obviously this formula is not working. Okay, so it's not working. All right, so this is the case where the wheel is spinning, but you're not going anywhere. The opposite is also true. Okay, so it's again an icy road and not a good experience. You step on the brakes, and guess what? Your wheel stops turning, but you keep moving. Okay, so very scary, right? Because you've lost control. So omega now is 0 because the wheel's not turning. The wheel stopped. You braked, so that stops the wheel from rotating. But the car is just still moving forward, so the axle of the wheel is still moving forward. So here you have some positive V, even though your omega is 0. And again, that formula breaks. The only time this formula is going to work, V is equal to R omega, is when the wheel is actually turning without slipping. And turning without slipping literally means that the point at which the wheel touches the ground has 0 velocity. The ground has 0 velocity, and the wheel just above the ground must also have 0 velocity at that point. Otherwise, the two velocities are different. It's slipping past one another. Okay, so that's, you don't have to rethink this every time. Okay, in the future, when we do problems and I say rolling without slipping, you can just pull out that formula. But you don't want to just, in a physics course, you don't want to just throw formulas at students without a deeper understanding. Like I try not to be tricky in problems, but if I said, look, you've got slipping going on, well then don't use this formula, because if you've got slipping going on, then it doesn't work. Okay, so now we can do a problem. Okay, so what is the velocity of whatever the object is at the bottom of the hill? Okay, so I'm going to have several parts of this. First, part A, no different than what we did when we did conservation of energy. Okay, so we have a hill here. Okay, and it's a frictionless surface, so we have energy is conserved. Friction is not turning energy into heat or anything like that. And I just have a block. The block is not going to rotate. It's going to start with a 0 velocity at point A here, and it's going to get to the bottom of the hill, point B here, and it's going to have some velocity, and it drops through a vertical distance h. Okay, we're going to do this problem without numbers. All right, it's easy to do without numbers, so we can do that. So there's no rotation here because it's just a block, and this block is just sliding downhill, and the hill is just a frictionless hill. If you want, you could think of it as a linear air track. Okay, something which will keep the mass floating on top of it, so there's minimal friction. All right, so conservation of energy. At point A, the energy is all potential, and so all gravitational potential, and so that's mgh. At point B, the energy is all kinetic. Okay, and so that's 1/2 mv squared. There's no 1/2 I omega squared because no rotation. All right, so here we go. Here's our initial energy, mgh. Here's our final energy, 1/2 mv squared. They must be equal one another. So we have mgh is equal to 1/2 mv squared. We're solving for v. That's our unknown. And so v is equal to the square root of 2gh. Okay, great. We've got a formula. Now, what are we going to do with this? If I gave you h, you could plug in here and you can find v. Okay, what we're going to do with this is we're going to compare it to some of the other formulas we get. Okay, so let's do this again. But now we're going to have a drum rolling downhill, or a wheel. It doesn't matter. It's a disc. Remember, the thickness doesn't make a difference. Okay, the drum has a mass capital M and a radius r. Okay, and as it rolls downhill, obviously it's rolling around an axis of rotation through the middle. Okay, it starts off with a velocity v at the top here, 0, and it gets to the bottom and it has a velocity v like that. That's what we're solving for, is that v. And I should have probably written here v is equal to question mark. And it also has a angular velocity omega, but we're not solving for omega. We really want to just get a formula for v there like that. Okay, so at point A, all the energy is potential, mgh. At point B, all the energy is kinetic, but there's two pieces now, the 1/2 mv squared and the 1/2 I omega squared. Okay, there we go. So at A, we still have mgh, and at B, we have 1/2 mv squared plus 1/2 I omega squared. By the way, I didn't mention this before, but this is not hard to remember at all, because remember how you go from linear quantities to angular quantities? For m, just replace it with I, and for v, just replace it with omega. So 1/2 mv squared becomes 1/2 I omega squared. Okay, so there we go. We've got the two contributions, the kinetic energy due to the center of mass and the kinetic energy due to the rotation of the center of mass. All right, so now what? Well, we've got a drum, and so the moment of inertia of the drum is 1/2 mr squared, okay? And if you look above, I gave you that formula. That was for the disk, but it doesn't matter what the thickness of the disk is, and so it's also true for a wheel or a drum, okay? Let's say a drum because it's uniform. Okay, so that I, that's where I got the 1/2 I omega, sorry, the 1/2 mr squared here, like that. That was for a drum. Now, what about the omega? So in this problem, we're assuming that the drum is rotating without slipping. It's rolling without slipping, and so in that case, we have that V is equal to R omega, the formula above. But now I want to rearrange it so that I have omega, and that's going to be omega is equal to VR. All right, so let me show you the formula above. Okay, whoops. V is equal to R omega. If I solve for omega here, if I isolate omega, that'll be omega is equal to V divided by R. And so down here, in omega, I'm going to substitute for omega V divided by R. Okay, oh, actually I had it right there. Okay, so that's no slipping. All right, so now what? Well, now let's simplify this. Notice that that R squared is going to cancel that R squared there. Okay, and so this is going to turn into 1/2 mv squared, that's this term right here, and then we've got a half times a half, which is a quarter. M, there's the R squared, and this is going to be V squared divided by R squared. The R squareds cancel. Collecting all the terms, we get 3/4 mv squared. So the energy can also be written as 3/4 mv squared, where V is the velocity, the center mass at point B, okay, at the bottom. Okay, since the energy at the bottom must equal the energy at the top, we have that mgh must equal 3/4 mv squared. And now solving for V, we get that V is equal to the square root of 4/3 gh for a drum. Okay, that's different, isn't it? That's different than what we got for a point mass, which was V is equal to the square root of 2gh. All right, so if you just got a mass and it doesn't rotate as it slides downhill, no friction. So you got a mass, it just slides downhill. How fast is it going at the bottom? Square root of 2gh. You've got a drum and it rolls downhill. Okay, when it gets to the bottom, how fast is it going? Square root of 4/3 gh. Okay, they're different from one another. I should just say one more thing about the friction. When it comes to the drum rolling downhill, notice I didn't say no friction there. We want just a little bit of friction so that it rolls without slipping, but not so much friction that we lose energy to heat. Okay, so I didn't put that this is a frictionless surface, because if this were a frictionless surface, then the drum would just slide downhill. So there's just enough friction to cause this thing to roll without slipping, but not so much friction that it's actually going to dissipate energy as heat. Okay, just thought I'd mention that for clarity. All right, whereas with the drum, with the block, we definitely had no friction at all. Now, when we compare these two formulas, we actually find that since 4/3 is like equal to 0.133333 and so on, that's less than 2. When we take the square root of both sides, we'll find that the square root of 4/3 gh is always less than the square root of 2gh, which is interesting. That says that when the drum rolls downhill, the drum is actually going to be going slower downhill than if it just slid down. All right. And you might say, well, why is that? What's going on? Why is the drum actually moving slower at the bottom than the block is? They're both the same mass. They're both dropping through the same vertical height. The only difference is that the drum is rotating when it gets to the bottom of the hill, whereas the block is not. And the answer is simple. The energy, you've only got so much energy, mgh. Okay? You've only got so much mgh, which is the same in both cases. But in the case of the block, it all went into 1/2 mv squared, because there was no other term. So all of the mgh goes into 1/2 mv squared. But when the drum rotates, some of that energy goes into the center of mass motion, but some of it also goes into the rotation. So the rotation is siphoning away a little bit of the energy that would have gone into linear motion. That means there's less energy in the linear motion, and that means it's moving slower at the bottom. It's kind of interesting. You maybe not expect it. Not that intuitive. Okay, so there we go. All right, so and I state that here, okay, because the for the drum, some of the mgh went into 1/2 I omega squared, leaving less for the 1/2 mv squared. Okay, therefore the drum is slower. Now, just to really drive the point home, I said do this again, but do it again now for a ball rolling downhill. And I probably should have said here, just to be very clear, a solid ball, or a solid sphere, not like a tennis ball, because a tennis ball is hollow. Okay, and that's actually a different formula. I could have given you that formula too, but I didn't want to overdo it. Okay, so now we have again the energy at the top mgh, the energy at the bottom 1/2 mv squared plus 1/2 I omega squared. Okay, and for omega, still v over r, but now I for a solid ball is 2/5 mr squared. Okay, and so working this out, you get a different factor in front here. You get 7/10, and so solving for v, you get that v is equal to the square root of 10/7 gh. Okay, now if you compare 10/7 to 4/3 to 2, 10/7 is 1.43, 4/3 is 0.33, like that. And so it turns out that if you compared a drum and a ball and a block going downhill, down the same hill, the block would be moving the fastest at the bottom, the drum would be moving the slowest at the bottom, and a ball would be somewhere in between. Okay, and that's kind of interesting. And there's a nice little demonstration that you could do even at home. You need 2 cans of soup. You need one can, which is chicken broth, which is just a liquid in the middle, and another one, which is cream of mushroom soup. Now, both cans have, say, 8 ounces of food in them. Okay, so they both weigh the same. They both have the same amount of mass there. It's just that the broth is liquid in the middle, and you can hear it slosh, but the cream of mushroom soup is solid. Okay, now you put both of them on the top of an inclined plane. Okay, like take a board, and you let go, and you say, which one's going to get to the bottom first? Okay, and the answer is the chicken broth gets there first. When it gets there, it's actually moving faster than when the cream of mushroom soup gets there. When the cream of mushroom soup gets to the bottom, it's moving slowest, so it gets there after the chicken broth. And you say, why? Why did that happen? Why does the chicken broth get to the bottom first? And the answer is, the secret is, that when the chicken broth rolls, it's the outside of the can that's rolling. The liquid in the middle, it rolls a little bit, but not as much as it has to with the cream of mushroom soup. With the cream of mushroom soup, it's all solid. Whereas with the chicken broth, it's mostly the outside that's turning, with less turning in the middle. And what does that mean? That means if you go back to this formula right here, sorry, where's that? Here we go. If you go back to this form, remember you've got mgh. Both of them have the same energy at the top because both weigh the same. They both have the same m, they both have the same h, and they're both going to fall through the same vertical distance h. Okay, so but now when they get to the bottom, the cream of mushroom soup is going to siphon off a lot more energy as rotational energy because all of the stuff is rotating. Whereas with the broth, only some of it is rotating, and so you have less rotational. If you have less rotational, you're going to have more linear kinetic energy, that is the center of mass. So the center of mass will be moving faster for the broth than it will for the cream of mushroom soup. If you don't have these soups at home, or if you don't feel like doing them, just go on YouTube, because there's lots of YouTube videos like this. It's a very dramatic experiment, and you can definitely see the physics behind this happening. Okay. One more topic and then we're done. Okay, and that's angular momentum. Okay, so that was the last topic we did last lecture before we went into rotational motion. So this is the last topic also for rotational motion. It's angular momentum. Okay, now you might wonder, why didn't we call it rotational momentum? Because we call it rotational kinetic energy, rotational momentum. I don't know. It's just called angular momentum. So, no good reason to change the name in this course. Okay. So, angular momentum is conserved, just like linear momentum is conserved. And so, just to remind you what linear momentum is, linear momentum was given the symbol capital P. And basically, you just you added up all the MVs. So you have like M1V1 plus M2V2 plus M3V3. You have a system of a bunch of masses M1, M2, M3. And you just add up the MV for every one of them, and that'll give you the total momentum. By the way, some of you might have seen the symbol sigma, like that. That symbol just means add up all the MVs. Okay, so add up all the MVs. All right, I'm not that I need it, but in case you know the symbol sigma, there it is. Okay. Well, angular momentum, same thing. It's given the symbol L, scripted L like that, scripted capital L like that. And now you're just going to add up all the I omegas. all the I omegas. And very easy formula to remember because mass m, the linear quantity, is replaced with its angular equivalent I. V is replaced with its angular equivalent omega. Okay, so mv becomes I omega. So you add up all the I omegas, and that's going to give you a total angular momentum, and that must be conserved. And you'll actually do this experiment in the lab, the very experiment that's inspired this example. Okay, so what we're going to have is there's a before and after picture. Remember, these are collisions. Momentum is useful for collisions. So now these are not going to be linear collisions like gliders colliding off of one another in an air track. These are going to be angular collisions. So we'll have things like a disk, which is spinning, okay, and I'm going to drop a rod on it, okay, and the rod and the disk will stick together, and then they'll be both rotating together. So my before picture shows a rod which is not rotating at all. So it has no angular velocity, omega is equal to 0, okay? And my disk is rotating, or it has some omega, which I give you a number down here, okay? And then I drop the two together, and they might slide at first, but eventually they'll stick, and they'll both be rotating. Both the rod and the disk will be rotating together with angular velocity omega prime. That is an angular velocity after the collision. Okay, so what are my numbers? A disk of mass 1.5 kilograms is spinning at 2.5 RPM. Okay, we drop a rod of mass 0.5 kilograms onto it as shown. All right, so let me scroll back down here. So here's my rod, a half-kilogram rod, and I'm going to drop it on there. How fast is the rod and discs? How fast are the rod and discs spinning after the collision? Okay, and the disc has a radius of 10 centimeters, and the rod has a length of 20 centimeters. Okay, so let's do it. And just like with linear momentum, remember I said as long as you're careful with the units and you keep the same units throughout, you don't have to convert to MKS. That's kind of useful, okay? In this case, it's kind of annoying to convert from RPM to radians per second and then back to RPM. So we're just going to work in RPM. And you say, why can you do that? Well, because omega comes in linearly. There's no omega squared. It's omega, 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 omega throughout on both sides of the equation. So if you have the same units on both sides of the equation, they cancel out on both sides of the equation. Okay, and so there's no reason to change the units. Let's make life easier for ourselves. All right, so before the collision, L is going to be the angular momentum of the disk plus the angular momentum of the rod. Okay, now for the angular momentum of the disk, we need I for the disk, and for disk, the moment of inertia is given by 1/2 mr squared, and we just plug in the numbers. The numbers, the mass was 1.5 kilograms, the radius was 10 centimeters or 0.1 meters, and so that gives us a moment of inertia for the disk of 0.0075 kilogram meters squared. Okay, the angular velocity for the disk, I tell you in the problem, is 2.5 RPM, and we'll just work in RPM for the reasons I just mentioned. Okay, now what about the rod? The moment of inertia of the rod, remember this is a rod, but now it's going to be rotating around its axis of rotation. And so the moment of inertia of the rod is 1/12, not 1/3. That's when it rotates around one of the endpoints. But when it rotates around the middle, it's 1/12 ml squared. So 1/12 ml squared, 1/12 ml squared for a rod rotating about its center. Okay, so substitute in the numbers. M is 0.5, L is 0.2 because the rod has a length of 20 centimeters, and that's 0.2 meters, and that works out to a moment of inertia of 0.00167 kilogram meters squared. Okay, and the rod is not rotating initially, so it has an angular velocity of 0 RPM. And so if we put this all together, we find that the rod has no contribution to the angular momentum before, and it's all coming from the disk. The disk, you multiply I times omega for the disk, and we get 0.01875 kilogram meters squared RPM. Funny units, but that's okay. The RPMs will cancel out. All right. So after the collision, the angular velocity of the disk and the angular velocity of the rod are the same. Okay. This is one of those collisions where things stick. When things stick, all the component pieces that are stuck together have the same velocity afterwards, whether it's linear velocity or angular velocity. Okay, and so our formula will simply be I of the disk plus I of the rod times the common angular velocity, which I'll just call omega primed. Okay, so omega of the disk and omega of the rod after the collision is the same, and we'll just call that omega prime. Okay, and so now just using the numbers above, the total angular momentum after is the same as before. So L primed, we can just substitute in L from before. That's the whole point of a conservation law. And I of the disk and I of the rod, we have those numbers above. Here they are. And the only unknown is omega primed. And so when we solve for omega primed, we will find that it comes out to be 2.04 RPM. Okay. Why revolutions per minute? Because all of our omegas are in revolutions per minute. Okay. Now I didn't put the units in there, but if I put the units in there on this side, we would have had kilogram meters squared RPM, and here we would just have kilogram meters squared. So the kilogram meter squared would have canceled out, leaving just the RPM. Okay. And so there we go. We get an answer that the common angular velocity is going to be 2.04 RPM. Does that make sense? Does it make sense? Well, where did we start off? How fast was it going? It was going at 2.5 before the collision, and after the collision, we expect it to slow down, and so sure enough, it slowed down from 2.5 to 2.04 RPM. Good. It fits our intuition. All right. So part B, I didn't put B there, but next part of the question, how much energy is lost as heat? Okay. This is an inelastic collision. Okay, whenever things stick together, remember I told you that energy is lost, and so energy must be lost here. It's an inelastic collision. Let's find out how much energy is lost. Okay, so in these problems, we only have rotational kinetic energy. All right, because the center of mass isn't going anywhere. The disk is spinning in place. The rod is spinning in place around their axis. Okay, and so all you have is the 1/2 I omega squared. And so the total energy here is just the kinetic energy due to the disk, but it's all rotational, the rotational kinetic energy of the disk, plus the rotational kinetic energy of the rod. Okay, in this case, we do have to convert from RPM to per second, and the reason is that we want our answer to come out in joules. If we don't convert, we're going to have some really weird energy units. So just to be clear, you've got a square there. Whenever you got squares, the units, you're going to have to convert the units. Whereas, see, with the conservation of momentum, all the omegas came in linear. So the units all canceled out, but they don't here. Okay, so we'll convert, but it's not that bad. The kinetic energy due to the disk is 1/2 the moment of inertia of the disk, which we have above, times the initial, so we'll do the initial kinetic energy. It's the initial angular velocity of the disk, which was at 2.5 RPM, revolutions per minute. Convert the revolutions to radians, convert the minutes to seconds, squared, plus 0. The rod isn't rotating initially, so the rod has 0 energy, contributes 0 energy initially. And so if we work that out, it turns out to be 0.000257 joules, which is annoying because there's a lot of zeros there. So I just wrote it as 0.257 millijoules. Okay, so that's our initial energy. That's our initial energy. What about the kinetic energy after? Well, the kinetic energy after is just the combined moments of inertia, both rotating at the same angular velocity. Okay, and so because it's all one thing rotating together. So whatever the total moment of inertia is, it's for the two pieces. You add the two pieces together, that gives you the total moment of inertia. Multiply that by its angular velocity squared, and you get the kinetic energy. So it's 1/2. Add the two moments of inertia multiplied by the angular velocity squared. Here I converted very quickly. It's 0.204 revolutions per minute. But to go from revolutions per minute to per second, radians per second, just multiply by 2 pi and divide by 60. That's actually what the upshot of all this is. See, you've got 2 pi on top and 60 on the bottom. Okay, so just to be very quick about this, there's the angular velocity in radians per second. Okay, and working that out, we find that this turns out to be 0.209 millijoules. So we started at 0.257 millijoules, and it went down to 0.209 millijoules, and so we lost 0.048 millijoules in this collision. That's how much heat would be generated. That's not a lot of energy. Like a joule is already not that big. A millijoule is tiny. Okay, and so this would, you'd be very hard pressed to measure this. Okay, by the way, next semester when we talk about heat, you'll see that we work with joules, and actually food energy can be measured in kilojoules. Okay, here in the US, if you take a look at like your chocolate bar, you look on the back and you see how many calories are in this chocolate bar, like 500 calories or something like that. In Europe, and I think in Canada, though I'm not sure, you would actually see that number in kilojoules. Okay, so a kilojoule is more like type of unit of energy that we would use for food energy. So a kilojoule is 1,000 joules. A millijoule is a thousandth of a joule. So we're talking about very, very little energy here. This would be almost impossible to measure in a lab. All right, so there we go. There's a problem using conservation of angular momentum, and it's very similar to one that you're going to do in the lab, because you're actually going to do this and you're going to measure the angular velocity before and after and see that if it works. Okay, so here's another one. I'm going to do two more problems with this. Okay, a merry-go-round of radius 2 meters and mass 100 kilograms is spinning at 5 rpm. Okay, so like on these child playgrounds, we've got these, like, this is like a platform that spins. Okay, and if you were like crazy like I was as a kid, you would make this thing spin as fast as possible, and you jump on and jump off like that. And so I don't know if they still have those because they were a bit they were a bit unsafe, but there they are. So I'm thinking of something like that. Okay, so a child of 50 kilograms, okay, is standing beside the merry-go-round and jumps onto it, landing 1.5 meters from the middle. So the merry-go-round has a radius of 2 meters. Okay, here I am trying to draw it in perspective. This is my before picture. And a child here, obviously with no velocity initially, jumps and lands 1.5 meters from the middle. And then, of course, when he jumps on, the merry-go-round and child both spin together with a common angular velocity omega primed. Okay, and I want to know by how much does it slow down and how much energy is lost. Okay, so very similar to the previous problem, only this time we're not dropping a rod onto the rotating disc. This child is jumping onto the rotating disc being the merry-go-round. All right, so before and after, very similar to the previous problem. We're going to have an angular momentum before, which is the angular momentum of the merry-go-round, mgr for short. Okay, and an angular momentum of the child. The merry-go-round is a disc. Okay, and it has a mass of 100 kilograms but a radius of 2 meters, so it has a total moment of inertia of 200 kilogram meters squared. Okay, its initial angular velocity is 5 rpm. Okay, and we'll work in rpm again. Okay, the child has no contribution initially, okay, because the child has no angular velocity initially. If the child has no velocity initially, right, standing on the side here, then the child has no angular velocity initially. All right, so all the angular momentum is due to the merry-go-round, and that turns out to be 1,000 kilogram meters squared rpm. Okay, after the collision, the child and the merry-go-round are rotating together, and so we'll have the combined angular velocity, I'll just call it omega. What we need, though, before we plug into this is we're going to need the moment of inertia of the child, and this is really why I did the problem. The moment of inertia of the child is just mr squared. You go, where did you get that formula? And here's the way to think about this. Okay, so let's go back to the diagram. When the child is on the merry-go-round here like that, think about the child, what the child is doing. The child is a point mass rotating at a distance of 1.5 meters. Now, when I did this example above, and I did it for, point masses in a line, I added m1 r1 squared plus m2 r2 squared. I had 4 masses. Okay, I had 4 masses. But you could do that with just one mass. Okay, there's no reason why there has to be many masses. If you have just one point mass m, rotating at a distance r from an axis of rotation, the moment of inertia of that mass is mr squared. Here we have just one mass, the child, 50 kilograms, rotating at a distance of 1.5 meters from the axis of rotation. So the moment of inertia of the child rotating around that axis is mr squared, where m is 50 and r is 1.5 meters. Okay, so this problem is very similar to the previous problems. You say, why are you doing it? Really, I did it for this right there. Okay. The child can be treated like a point mass. So m is 50 kilograms, r is 1.5 meters. That means that the child has a moment of inertia of 112.5 kilogram meters squared. Okay. The total angular momentum after the collision, L prime, is going to be the combined moment of inertia of the child in the merry-go-round multiplied by their common angular velocity. Okay, so angular momentum is conserved from above, 1,000 kilogram meters squared RPM. That's what we found for the system before, and so it's the same after. That's going to equal the combined moment of inertia. Remember, it's I omega for one time plus I omega for the other. But since the omega is the same, you could just factor it out. That's what happened here. Okay, so we have I for the merry-go-round plus I for the child multiplied by their common velocity. And you're working this out, it turns out that the common angular velocity is 3.2 RPM. So basically, the merry-go-round slowed down from 5 RPM to 3.2 RPM when the child jumped on it. Okay, makes sense because now there's more stuff rotating, so it had to slow down. Okay, now the energy before is just the energy because of the rotating merry-go-round. So I have 1/2 I omega squared calculated just for the merry-go-round. And again, just like above, moment of inertia was 200 kilogram meters squared for the merry-go-round. And then the 5 we had to convert to radians per second. And that turns out to be 27.4 joules. Okay, so this merry-go-round rotating has only 27.4 joules. Again, it's a pretty heavy merry-go-round, 100 kilograms, and yet it only has 27.4 joules of energy in it. Okay, so what about the energy after? Well, the energy after is going to be the energy of the combined merry-go-round and the child. Okay, 1/2 I omega squared, where now I is the combined moment of inertia, merry-go-round and child, and omega prime is common between the two. Okay, so it's 1/2. The combined I is the 200 plus 112.5, and the omega, converting it to radians per second, is 3.2 times the converting factor, and that gives us 17.5 joules. Okay, so the energy lost to heat, and I put heat in quotes here, and you'll see why in a minute, is going to be 27.4 minus 17.5. It's 9.9 joules. So you lose 9.9 joules during this inelastic collision. Okay, here's why this problem is really interesting. Here's another reason why I gave you the problem. What do you think happens as the child starts to walk towards the middle of the merry-go-round and then actually lands up in the middle of the merry-go-round? Okay, it turns out that the merry-go-round starts to spin faster. And you go, why is that? Well, have you ever seen a figure skater when they're doing a spiral and they pull their arm in? When they pull their arms in, what happens? They spin faster and faster and faster. So as the mass gets pulled towards the middle, it turns out that the figure skater rotates faster. Why? Well, what's the angular momentum? It's I times omega. And that I times omega has got to be fixed. Okay, so it's got to give a fixed number because it's conserved. If I decreases, if you pull in your arms, your I gets smaller. If your I gets smaller, but I times omega has to still be the same number, I get small, omega has to get bigger to compensate for the I getting smaller. And that's what happens when a figure skater pulls in their arms. They pull in their arms, I get smaller, but their omega has to get bigger. If they pull in their arms enough, omega is going to get significantly bigger, and that's where you get the really fast spinning. Okay, this is the same thing that's happening here, but I guess to a lesser degree. The child is out here. As the child moves into the middle, what happens to their moment of inertia? When the child is right at the middle, their r is 0, their moment of inertia is 0. Okay, so the moment of inertia decreases, the total moment of inertia decreases from before to after, so the omega has to increase. Okay, so let's work that out. Okay, when the child is at the center, I say that here, when the child is at the center, the moment of inertia of the child is 0. So the before is the same. So we have the total angular momentum before. That's that 1,000 kilogram meters squared RPM. Okay, so I'm not going to recalculate that because it's the same. So my moment of inertia, my angular momentum after is still the same number. The moment of inertia for the merry-go-round is 200. The omega for the merry-go-round is going to be omega prime. The child has no contribution now because the child has a moment of inertia of 0. Okay, and now if we calculate the angular velocity once the child has walked to the middle, it turns out to be 5 RPM again. So when the child jumped on, it slowed down to 3.2 RPM, but when the child walked to the middle, it sped back up to 5 RPM. That's why I put heat in brackets up above, because the energy is never really lost. It just kind of hides itself in different places, okay? And you didn't see where that energy was, but it was still there, and you got it back, because as soon as the child walks to the center, you're back to the same energy as you had at the beginning, because you're back to the same energy, same angular velocity that you were at the beginning. Okay, this is kind of interesting. All right, so the merry-go-round basically speeds up to its original speed. Okay, and here I also noticed that it's like a figure skater pulling in her arms. Okay, all right, last problem. Okay, so I wanted to do 3 problems for angular momentum, because this third problem shows the equivalency between linear momentum and angular momentum. Okay, so like all through this, I've been talking about rotational motion and so on, but really all of these things are just linear quantities, but in disguise, or recast. So like tau net equals I alpha, that's just F net equals ma, but in recast into angular terms. The same thing with angular momentum. It turns out that angular momentum and linear momentum really are the same thing. It's just you take the linear momentum, you recast it into another form, into angular quantities, and you get your conservation of angular momentum. And this problem is going to show you that. Okay, so what I have here is a rod. Okay, and the rod, is has an axis of rotation up at the top. Again, you could think of this as like maybe a stick with a nail, and if it can freely spin around that nail like that. Okay, and what I'm going to do is I have this rod here like that, and I'm going to shoot a bullet into it. So the rod is not moving, and the bullet's going to come in, and as soon as the bullet hits the rod, it's going to get embedded in the rod. Okay, well, you know what's going to happen. The bullet and the rod and the bullet embedded in it are going to start spinning like that. Okay, and I want to know how fast is the rod and bullet spinning after the collision. So before the collision, there's just a bullet moving in a straight line. After the collision, the bullet and the rod are rotating. Okay, and you could see that this is both a linear and angular momentum problem. Why? Because before the collision, all the momentum is linear. The bullet is just moving in a straight line. And then after the collision, it's angular. And you go, well, wait a sec, you didn't give me a formula that equates angular and linear, so how do I connect the two? Well, we'll see. Okay, so let me just give you a little bit of the English here. A bullet of mass 5 grams is traveling at 500 meters per second. Okay, it strikes a rod as shown, 1.5 meters from the axis around which it can spin. Okay, the rod has a length of 2 meters and a mass of ½ kilogram. So just to be clear, the rod here like that is 2 meters long, but the bullet strikes 1.5 meters from the axis. Okay, and I want to know how fast is the rod and bullet spinning after the collision, afterwards. All right, so before, all the momentum is linear, after it's all angular. All right, so the trick here is to see how the linear and the angular velocity really are the same. Okay, and the way to see that is at the moment of the collision. So if you just follow the trajectory of the bullet is first going along a straight line, and then all of a sudden it switches from straight line to circular. Okay, so let's think about what happens at that point where it's switching from straight line to circular. All right, at the point where it's turning from straight line to circular, but when it's straight, you could think about it having a linear velocity v. Okay, but when it's circular, it has an angular velocity omega. We can relate that angular velocity to the linear velocity because v is equal to r omega. Okay, so we're going to use v is equal to r omega to translate between our linear quantity and our angular quantity. All right, so I don't want you to think about it when it's right on the circle, because obviously after it hits the rod, it's going to slow down. Think about it just before it hits the rod, just before. So it's still on the straight line. It's still traveling at 500 meters per second. It's still on the straight line, but it's also just starting on the curve. And so we can convert that 500 meters per second linear velocity into its equivalent angular velocity on the curve with radius r is equal to 1.5 meters. Okay, I hope that's kind of clear. Okay, there's an equivalency between that linear velocity and the circular path, the angular velocity, even even up to the instant before the bullet hits the rod. Okay, and so over here we're going to use v is equal to r omega, or omega is equal to v over r. Okay, so I actually say it here. Before the bullet hits the rod, it has an angular velocity. So it's just before, and so you can think about it as just starting on that circular path, and that angular velocity is just v over r. And so that's 500 meters per second divided by 1.5 meters, because that's the radius at which the bullet strikes. And so 500 meters per second divided by 1.5 meters gives you 333.3 per second. You'll notice the meters cancel out. You get per second, which is exactly the units per omega. Okay? And so now we can calculate the total angular momentum before, because we don't have linear velocity anymore. We've converted from the linear velocity v to an angular velocity. Okay? So the total angular momentum before is the angular momentum of the bullet plus the angular momentum of the rod. But the rod's not doing anything before the collision, and so the rod has no contribution to the angular momentum. It's all bullet. Okay, the bullet, the moment of inertia of the bullet is just before it strikes. It's a mass m at a radius r. Okay, so just picture that bullet just before it touches the rod. It has a mass m, and it's at a radius of r. It has a mass of 5 grams, and it's at a radius of 1.5 meters from the axis of rotation. And so its moment of inertia is mr squared. This is just like the point mass of the child in the previous problem, mr squared. M is 0.005 kilograms. Okay, it's 5 grams. And r is 1.5 meters, and that gives us a moment of inertia of 0.01125 kilogram meters squared. Okay, and so plug that into our formula here, because we need I and omega. So we have I now. Okay, there it is. We have omega. There it is. Multiply the two together, and you get a total angular momentum of, before the collision, of 3.75 kilogram meters squared per second. Okay, those are the units of angular momentum, kilogram meters squared per second. There's no abbreviated unit for it. Okay, it looks like a funny unit, but there it is. Okay, after the collision, what do you have? You have both the rod and the bullet rotating with a common angular velocity. We'll call that common angular velocity omega primed here, like that. And then factoring that out, of course, then you'll just get the total moment of inertia is the moment of inertia of the bullet plus the rod. Okay. Well, we don't have the moment of inertia of the rod, but that's easy enough. It's a rod rotating around an axis at one end, which is 1/3 ml squared. Plugging in the values, the mass of the rod was 0.5 kilogram, I said above, and the length was 2 meters, and that gives us a moment of inertia of the rod of 0.667 kilogram meters squared. And so now, I probably should have rewritten this formula here, but L primed, that's your angular momentum. It's the same before and after, and that's going to be your, let's see, we calculated here, that's your 3.75. So 3.75, the total angular momentum, is equal to the sum of the two moments of inertia multiplied by their common angular velocity, sorry. And then that gives you the angular velocity of 5.53 per second. Okay, so there you go. There it is in omega. That answers the question, okay, in per second. But I wanted to convert it to RPM, because RPM is maybe a little bit easier to picture in our minds. It's like, how many times is this thing going to spin per minute? Okay, and so converting it, it gives you 52.9 RPM. All right, and that means in 1 minute, it's going to turn roughly 53 times. Round that off to 60. It's going to turn 60 times in 1 minute. That means like 1 turn per second. Okay, so when this thing hits, the bullet's going to cause this thing to rotate once every second. Okay, and that's how fast the rod will spin. That kind of makes sense. Okay, it's a small bullet. It's only 5 grams, and it's traveling at 500 meters per second, which is pretty fast. Okay, it's faster than the speed of sound. But I'm not sure how fast bullets travel from guns, but I can imagine that they might be a lot more than that. But there you go. There it is. Okay, so this entire lecture was all about rotational motion, right? From kinematics to dynamics to conservation of energy to conservation of angular momentum. All right, thank you very much for listening, and that's it.